So the next talk is titled MVAPICH2 on Thor, high performance MPI meets mainstream Ethernet controller. And yesterday we had the tutorial from Broadcom folks, both Hemal and Mose were there. They introduced the adapter, the MVAPICH2 on Thor, the Thor and the associated designs. So today they will be trying to go more into the performance for MVAPICH2. So let me quickly introduce Hemal Shah. He is a distinguished engineer and system software standards architect in the CCX division at Broadcom. He leads and manages team of architects. He is responsible for the definition of Ethernet NIC product architecture and software roadmap architecture for performance NICs and smart NICs. Mose Bholoshin is a system architect also in the same division. He spearheaded the system architecture development of ROCE and congestion control in Broadcom NICs, involved in the definition of Ethernet NIC product architecture, performance NICs, smart NICs, modeling and system simulations. Devesh Sharma is a software engineer at Broadcom in the CCX division. He has worked on RDMA technology for more than 14 years. During this course of time, he led the development of the ROCE driver and RDMA provider library for several generations of multiple Ethernet controller product lines. So with this, let's welcome all three of you. If you people can get started with sharing your screen and please start with the presentation.
Thank you, Dr. Panda. Can you see what I'm sharing?
Yes, it is there.
Okay.
Looks good. Yeah.
All right. So in this talk, as you mentioned yesterday, we introduced Thor, Broadcom's 200 gig Ethernet controller, targeted for mainstream market as well as HPC. And we went over our ROCE feature set, as well as congestion control and other architectural components in details yesterday. So in this talk, what I'm going to do is I'm just going to quickly recap Thor, and then we will directly jump into some of the initial performance results we have across multiple benchmarks as well as HPC application. And at that point, I'll transition it to Devesh, who will go over those results. So that's pretty much is the agenda. So just to recap, Thor is Broadcom's latest Ethernet controller. This is our 4th generation Ethernet controller. This is 200 gig throughput capable device. It has very high packet forwarding rate and very low chip latency. And it's the first one with the support for PCIe Gen 4. It has also a very high scale SRIV support as well as multi-host support. In terms of network connectivity, it supports various different configuration of number of ports as well as how they're used with different SerDes lane, whether it's NRZ or PAM4. And specifically on ROCE, this is a very highly optimized device for low latency, high performance RDMA implementation. Focus is on ROCE v2. And for the large scale, we added a lot of feature set in the hardware for congestion control, latency optimization, and we went over those in yesterday's talk. So this is a scorecard of all the baseline ROCE hardware feature. I'd already talked about the speeds and feeds, as well as the large scale of SRIV function. It also combines ROCE implementation with hierarchical scheduling, which allows you to QoS from per QP to per function, as well as at the port level. That's why it's hierarchical. For the congestion control, it has a flexible scheme in there, which allows you to have probabilistic as well as deterministic marking scheme based on standard ECN capabilities. In terms of connection types, you can think all the standard ones, including reliable connections, unreliable datagram, and raw ether type QP support. Very wide support for memory management and protection, and large scale of resources in terms of QPs, million. Combining with that is the number of CQs that go along with that, as well as shared receive queues that are supported 64K. In terms of high application level scaling, it has a large scale of doorbell pages or DPI, which allows you to have large number of processes sharing the NIC with the protection provided by the device. So this is a quick overview of all the baseline ROCE features. And then especially with Thor compared to the previous generation of RDMA ROCE implementation, Thor added number of enhancements which are listed here. I already mentioned the congestion control supporting the hardware, which is highly scalable in terms of how many number of competing flows you can support. It supports hardware-based ECN marking as well as reaction point in the hardware on per QP basis. So that's for the scale. For the improvement of latency, the device supports caching of cookies, and it applies to different types of cookies. This improves the performance. Number of DPIs, this is for large scale applications where you want to have higher number of protection, doorbell level, page level protection that supports that. And for PFC and other mechanism here, there were a couple of enhancements to monitor PFC traffic and have watchdog implementation, which prevents the flood of PFC on the network, as well as ability to support PFC asymmetrically. This is supporting switch environment where independently from what price are enabled with PFC, you want to have flow control all the price on the network. And so those are all supported in the hardware. And then for HPC database type of application where there is a model where you want to have one shared protection domain, and within that have a very large contiguous memory region that can be used for application scaling. So multiple cooperating processes can share those. So that support was introduced in Thor to enable that model. And while doing all these data path features, we also added a number of features which allow you to have visibility into the traffic. And that's where a lot of statistic monitoring and per cost queue level counters were added. So this allows you to have more visibility into the ROCE traffic. So these are all the advanced features that are in Thor. And our philosophy has been enable this with the standard open source RDMA stack. So this shows you the Thor ROCE software support on Linux. Basically what it is involving is the user mode library. Along with that goes the ROCE driver, which is coupled with the L2 driver where it provides the basic NIC functionality. And the control plane firmware, which basically abstracts all the hardware resources, provides the isolation, protection, and virtualization of the underlying hardware resources that are used by one or more function driver. And this stack, independently from what environment it's in the bare metal to a VM or a container, the driver model stays the same. And it's the same driver, whether it's used over a physical function or virtual function. So overall, this architecture is aligned with the open source RDMA stack that Linux kernel supports, as well as supported by the OFED distro. And on top of this software architecture, you basically build your MVAPICH or any MPI stack. Basically, it builds on standard Verbs stacks and enables MPI application without requiring any modification to the application or any proprietary Verbs extension. So that's very quick overview of the device, Thor, which is our 200 gig Ethernet controller that supports ROCE v2, and then all the software support that goes along with that. Next, the rest of the talk will spend on actually showing the preliminary data we have on Thor, very promising in terms of the microbenchmark results as well as HPC application and scaling data. Our focus is to share that data, not to compare to MPI implementation, but you will see we have both MVAPICH2 and Open MPI and numbers that you will see in the charts later. And the scaling wise, due to the cluster scale availability, we have results up to 8 nodes, but in the future, we are planning to have more scale performance as well as variety of other application performance results for the MPI community. So that'll be coming in the future. With that, let me hand it to Devesh, who will, I'm going to share the slide deck, and Devesh is going to go over all the results that we have. So Devesh.
Yeah. Hello, everyone. Do you hear me well?
Yes, yes.
Yes.
Okay, thank you. So here I would like to start with the Verbs level performance, which is the baseline we have right now. This is a little brief about the setup we have used. We used Intel Gold Xeon processor with 2 sockets and 32 cores each socket. So here you can see that for Thor is reaching line rate for 2 QPs and more than 2 QPs. However, for the single QP, we are still reaching to 80 Gbps, around 80 Gbps in the small message range, and for the large message range, we are reaching to line rate for more than 1 QP at the MTU size, and for the single QP, we are touching the line rate around 256K kilobytes or somewhere in that range. I would also like to present give you the overview of the latency which we are facing, which we are seeing. So this is round trip by 2 latency, and for RDMA write, and we are seeing 1.93 microseconds, and this is agnostic of what is the MTU size used when the tests are run. Next slide, please. Okay, so now I would like to take you to the OSU benchmarks which are at MPI level, and in this section I will be presenting you some basic MPI level tests which are unidirectional by bandwidth, then latency and the message rate, and the bidirectional bandwidth. The setup which we have used here is 2 nodes connected back to back, connected via switch. Each host has 1 Thor adapter, and the MPI which we have used here is MVAPICH 2.3.5 pre-release, which has Broadcom adapter support, and Open MPI 4.0.3 with UCX 1.8.1. Next slide, please. So here, if you take a look at the bandwidth numbers for the small messages with MVAPICH2, we are performing really well. The Thor performs really well, and it reaches to line rate around 256 kilobytes, even with the MPI layer in between. And at the latency, with the MPI, we are around 2.1 microseconds, which is well below 3 microseconds. And for the message rate, small message sizes, the performance is really good. With MVAPICH2, we see that it is somewhere near 2.3 in the range of 2 million packets per second for the range of 2 bytes to 32 bytes. And then even after that, we are seeing good performance numbers, but at some point around 2 kilobytes, we are seeing it is meeting to the Open MPI numbers. So the net bottom line is that Thor is performing really well with MVAPICH2 and Open MPI, and it is all set for to be used for the HPC kind of workloads. Next slide, please. So this is the bidirectional bandwidth for small messages. We are seeing the numbers are the curves are really smooth, and with MVAPICH2 we are seeing for small messages the numbers are really good, and for the large messages we are performing well for both the MPIs, and there are not much differences between any of between um, the MPIs. Next slide, please. So now I will turn my focus to the MPI collectives. These are 8-node setup with the same CPU which we have used for the micro benchmarking, and this section will detail about the collective communication. Here the MPI used is MVAPICH2 2.3.5, and the main areas which I will be focusing is are non-reduction operations, basically scatter and gather. All reduce operation, which involves the reduction operation, and the numbers are presented for 2, 4, and 8 nodes. There are a couple of optimizations we have used when we were running the test with MVAPICH2 listed here. Next slide, please. Okay, so on the left hand side there are numbers for OSU gather benchmark, and each of them each curve you see here is belonging to 2 nodes, 4 nodes, and 8 nodes. So if you see here we are getting really good and smooth curves, and the latencies are not that much high. So for 8 nodes, we are somewhere around below 6 microseconds, and likewise for and the yellow line is for 8 nodes. So up to for 8 nodes we are 8 nodes and 4K message size, we are around 6 microseconds below than 6 microseconds, and for 4 nodes we are slightly above 5 microseconds, and likewise for 2 nodes we are seeing latency which is in between 5 to 4 microseconds, somewhere there. Similarly, if we look at the scatter, which is one to many, for 2 node and 4 node we are seeing really good numbers, and the latency is really low. However, for 8 nodes we are seeing some anomaly here which needs to be further which will be tuned in future. So the so for small messages, both the basic operations, MPI operations, are scaling really well. Next slide, please.
Hey, Devesh, one quick point also I want to make on the gather. For 512 byte or less, the latency is between 1 to 2 microsecond, which is really interesting to see here how it stays flat till that point.
Yeah, yes.
Okay.
Okay, so this particular slide details about all reduce operation, again with 2 nodes, 4 node, and 8 nodes. So here the latency for 2 nodes is below 40 microseconds at 4K message size. However, we are seeing a little anomaly at 512 processes, which is 8 nodes, 4 kilobytes of message size. But as we are sharing these preliminary numbers, this particular anomaly will be addressed in future, and as we go on and do more and more tuning, we will be getting rid of this particular bump here. Other than that, for the range of 32 bytes to 2 kilobytes, we are scaling really well, and the latencies are below 50 microseconds, or nearing to 40 microseconds in the 8 node case. So so reduction operation as such is scaling really well on Thor with MVAPICH2. So with this, I would like to move to the next slide. So here there are some HPC applications which we have run on an 8 node cluster. So there are 8 nodes which are connected via switch, and the switch is configured for PFC. However, Thor has other features also, as Himal has presented in his presentation. But for now, this is configured for PFC. Each node has one Thor adapter connected to a PCI Gen 4 slot. The MPI which we have used is 2.3.5 pre-release and OpenMPI 4.0.3 with UCX 1.8.1. We are running here NAS parallel benchmark with class D, a mini application, mini host, and Cloverleaf tip of the GitHub for both mini host and Cloverleaf applications. NAS benchmark class D we have used, and the sub benchmarks which we have selected here are LU, BT, SP, and CG. So because LU, BT, and SP, they need a square number of processes. These are limited to 484 processes, while CG can be run for power of 2 processes. So that we have run for 512 processes on 8 node. For 4 nodes, the number of processes are 256 for each test, and for 2 nodes it is again LU, BT, SP is for 121 processes and CG is for 128. Similarly, mini host has been run for 512 processes when it was run on 8 nodes, and 256 processes when it was run on 4 nodes, and 128 process when it was run on 2 nodes. For Cloverleaf, we have used BM512 short problem size, which usually, I mean, on the average, it takes around 2 minutes of runtime. So this is all about setup. If we can move to the next slide. I can detail about, so okay, so here the first on the top left is NAS BT. So if we look at this, the trend line shows that the scaling with both the MPIs is really well. With 2 nodes, we are taking somewhere around 430 to 440 seconds of runtime. And as we keep on increasing the number of nodes, the the execution time is going down linearly. In the BT, especially if we look, I mean, it is available, it is across the board. But for 2 nodes with MVAPICH2, we are seeing slightly bump in the execution time. But if we go down and keep on looking into the number, keep on increasing the number of nodes, we see that with 8 nodes, MVAPICH2 is really scaling well. This particular fact is applicable to LU as well as to CG and for SP we are not seeing this, but probably with the in the near future with more tuning, we will be able to get better results with more bigger scale. So now Cloverleaf, if we look at this one, is a application which scales really well. With and Thor shows really good results in terms of execution time with the number of nodes. So if we look at 2 nodes performance, we are somewhere around 250 seconds, and the time decreases linearly as we increase the number of nodes. And for 8 nodes, we are somewhere around 62 seconds to complete the same problem, which took 250 seconds in 2 nodes. MiniGhost is a weak scaling application, and this hardly gives any improvement when we increase the number of nodes, which is evident here. So we are somewhere around 125 seconds with MVAPICH2 and 130, 120, 28 point few seconds with Open MPI, and this time hardly changes along as we increase the number of nodes, and we are almost equal for 4 nodes and 8 nodes, which is somewhere around 122 seconds. So one of them I missed. I guess I missed to talk about CG. So CG is showing really very good results here. If you look at 2 nodes performance with the MVAPICH2, and this is not with too much of tuning. This is basically just we have taken the Thor drivers and configured it for PFC, and we have just run it. Not very particular, except for the CPU placement. We haven't done any tuning here, and still we are getting very good results with 2 nodes. The CG problem finishes in 150 seconds, and 4 node, same problem, the class D size problem finishes in within 110 seconds or somewhere there. And for 8 nodes, it is really very good, which is somewhere around 62 seconds. So with this, the key takeaway here is that Thor is scaling really well with most of the applications which usually are used in HPC application domain. And this demonstrate a real capability at the 100G speed of Thor adapter. So this is all I have. Yeah, are there any questions?
I don't see any questions in the Q&A box, but I think both the ways you indicated, like a lot of these things, one has to take care of tunings, especially collectives. As many of you know, like there are many different algorithms. So based on the system, architecture detection and all, these can be tuned to get even better performance.
Yeah.
So there is one question on the QA box. If you do that, I'll read why is gather latency so much larger than scatter latency?
Okay. So that is as we have said that these are some preliminary numbers, and we haven't done. I mean, we are still trying to fine tune it. So the things are still under. Some things are still under investigation. Probably we can take it as a follow up in the coming in the near future.
Yeah, I can also add a comment here. I think you are reporting with the OSU Microbenchmark, so that has average, mean, and max. So gather and scatter are opposite. Like gather, if you see the communication pattern is all the processes are sending data to one node. Scatter is one going from the outside. So depending on the network topology and what is happening, how much components communication is happening intranode versus internode, the average latency may change. So you may need to take a look at the max latency, min latency, and see. And then on top of that, you need to adjust the algorithms to get the best performance.
Yeah, that's a good point, Dr. Panda. So in general, but we wanted to show the initial results here. There's a lot of this is the goal is to show with the standard drivers we are starting on a very strong foot, and then there's further room for improvement. So welcome any input on how to tune this, how to. Our goal is to make Ethernet applicable to this mainstream HPC market, right? And we are with Thor. We are at a point where we don't see significant difference between InfiniBand and Ethernet for most of the apps.
There are 2 additional questions. Can you people take a look in the QA box? So
sure. I'll stop sharing here. Was the message rate, one question, 2 million, this is 100x lower versus other option. I think you are referring to the message rate on the one of the message rate we showed. That was for the point-to-point benchmark. So this is at the application level. The other option, 100x lower, what you're referring to is the device is capable of 100 million packet per second rate. This is more at the application level, and we are going to investigate what are the other software overhead which is contributing to that. So that's a quick answer to that. There's another question. Will Thor HPA bandwidth increase if you connect both ports? Yes, we support 2x100 gig. In that case, Thor bandwidth will go to 200 gig in each direction. One of the challenge is also today without the Gen 4 production platform availability, primarily we can test with 100 gig. That's why you are seeing the 100 gig numbers. Once we have all the Gen 4, PCI Gen 4 platform numbers, we will be able to show 200 gig.
Okay, so I don't see any other questions or in the slide.